Hello everyone, we are the Group 3 of ECE5553, Autonomy in Vehicles, from the Ohio State University. In this video, we are going to briefly introduce you about our final project.
The goal of this project is to design a low-speed autonomous shuttle that will be able to transport passengers around Easton Town Center. The shuttle must use path planning, collision avoidance, localization and perception, and a decision-making algorithm must be designed to control the shuttle.
Hi, I'm Nick Vallow, and I'm going to be talking about our choice of an autonomous vehicle. When it came to longitudinal dynamics, we chose a mass of 3,450 kilograms, which we found from an existing data sheet found in reference number 2. We also used proportional reasoning for many of these new parameters. Compared to the earlier sedan model done on Homer 2, we changed the wheel moment of inertia to 1.5 kilogram meters squared, the wheel radius to 0.45 meters, aerodynamic drag to 0.45, frontal area to 5.2 meters squared due to the increased size of the vehicle. Longitudinal stiffness we changed to 4 times 10 to the 5th newtons, which the reasoning for that was due to the fact that buses have larger tires, therefore the stiffness and there is a larger wheel radius than the sedan model, and a cornering stiffness of 1.8 times 10 to the 5th. Lateral dynamics, we used the same rationale as with the longitudinal dynamics model. We chose a vehicle that is 4.0 meters long, with a front axle that is 1.8 meters from the center of gravity. The rear axle is 2.2 meters from the center of gravity. The yaw moment of inertia was found using proportional reasoning with the vehicle masses between this shuttle and the 2,000 kilogram sedan, and it was found to be 6,400 kilograms per meter squared. The desired velocity was also set to be 6.7056 meters per second, which translates to 15 miles per hour, the speed limit at Easton.
I'm Hao Chen, and I'm gonna talk about the autonomous vehicle architecture. In our designing, a GPS chip will guide the vehicle to follow the road. LiDAR and radar system will help in avoid obstacles. Cameras are used to recognize objects. To avoid collisions, 8 ultrasonic sensors will be added on the sides. The figure below shows the sensors placement of our vehicle. One camera will be used for the automated door. From the sensors range plot, we can see the radar is mainly focusing in the front. LiDAR system will be sweeping around to have the 360 view of the vehicle. Ultrasonic sensors are designed to avoid collisions, especially when the vehicle is turning.
Here are our results for the longitudinal control modeling. For the low-level longitudinal control, a Simulink model was made. Actually, 2 models were made, one for speed and one for braking response. A PID controller was added to the input, which takes in a desired velocity, v_des, as well as a negative feedback from the current velocity. The PID controller is tuned to P equals 115, I equals 2.2, and D equals 25, with N, the filter coefficient, equaling 10. The desired velocity, v_des, is set to 6.7056 meters per second, which is 15 miles per hour, the speed limit at Easton. The results can be seen in the plots to the left. In the upper plot, you can see the velocity response accelerates to just around under 15 miles per hour in 10 seconds and never goes over the legal speed limit or the vehicle speed limit. In the bottom plot, you can see that a braking torque gets applied at time 15 seconds of 80 Newton meters until the vehicle slows down to a stop at around time 22 seconds. Now it's time for lateral control. Low-level lateral control model, Simulink governs the velocity, dynamics, tire modeling, and kinematics of the vehicle. The velocity is controlled to follow a desired velocity, here set to VDES equals 6.7054 meters per second, or 15 miles per hour, the speed limit at Easton. The steering angle for the front tires, delta F, is stepped from 0 to 3 degrees at time 1 second. For the results of the model, you can see in the top plot that the vehicle achieves successful speed regulation. Throughout its operation, it stays even with the legal speed limit of 15 miles per hour and never exceeds it. In the bottom left plot, you can see the slide slip angle stays at a constant steady state, indicating that it never exceeds the steering angle limitations of the vehicle. The yaw rate in the lower right plot also shows this, as it achieves steady state as well.
Hello, my name is Sean Burns. I'll be talking about the path planning and filing model. The model used for the path planning simulation is very similar to the one done in Homework 4. The Easton shuttle bus route was plotted as a bunch of points, which was used to generate many Bezier curves. This path was then used to calculate the road curvature difference. Based off of this information, the steering wheel input and the trajectory of the vehicle were then simulated for the whole route. The simulation ends when the bus has traveled the entire distance of the route. Shown on this slide is the reference path of the shuttle route and the actual path the shuttle takes. The graph on the right shows the steering wheel input, the road curvature difference, and the calculated error against time of the simulation. Throughout the entire simulation, the bus travels at 15 miles per hour.
I'm Will Casey. I'm going to talk about the collision avoidance system used in this project. The system used was adapted from Homework Unit 9 of this course. This is the adapted block diagram from Homework Unit 9. The speed limit was changed to 15 miles per hour to meet the speed limit of the route. The Ego vehicle model was updated with a longitudinal model designed specifically for this shuttle, and the behavior of the other car in the simulation was altered slightly to accommodate those two things. There are 3 states for the collision avoidance system. State 0 has the vehicle follow the speed limit when there are no obstacles detected. State 1 has the vehicle match the speed of a slower moving vehicle in front of it. And State 2 has the Ego vehicle stop if an object has gotten too close. This is the response with an additional vehicle with oscillating speed initially in front of the Ego vehicle. Later in the simulation, that vehicle pulls away, and then the Ego vehicle encounters another object that was blocking the road. The desired speed is adjusted based on the distance to these obstacles and the speed of the obstacles. This is the simulated response of the vehicle with the desired speed inputs. This response was obtained using the longitudinal vehicle model. The model was well made, so the acceleration and deceleration is fairly smooth. The last brake maneuver is a little steep, but that's because it's an emergency braking maneuver.
Hello, I'm Shiming Shao, and I'm going to present the problem of localization and perception. The first example is detecting obstacles by multiple sensors. In this model, it can detect obstacles in the range of different sensors. You can see the red arrow is the range of the radar detection, and the blue arrow is the range of vision detection. And the model can display its obstacles by using a bird eye view. And this model is powered by Automatic Driving System Toolbox. The second example is detecting obstacles by LiDAR. In this model, it can detect obstacles by using a 3D LiDAR and display the obstacles by plotting points cloud. We can use the shape of the points cloud to detect the obstacles is vehicle or something else or the pedestrians. And this model is powered by Automatic Driving System Toolbox. The third model is detecting vehicles in pictures, which is powered by Automatic Driving System Toolbox. And In this model, it can detect the vehicles in front of the illegal vehicles by using pictures and track them by a yellow block. This model is very similar to the previous model, which can detect vehicles in pictures. So we can use this model to detect multiple vehicles on highway simultaneously. This model can be used to detect vehicles in visual front camera. So that means we can use this model to detect and track the multiple vehicles simultaneously and dynamically by using a camera in front of our automatic vehicle. And the next one is detecting pedestrians in video from cameras. So in this model, we can use a camera to detect and track the pedestrians in front of us. And this one is also detecting pedestrians in visual from camera. This can also detect and track the pedestrians by a colorful block, but different from the previous model, which is powered by automatic driving system toolbox. This model belongs to computer vision system toolbox. The last example is detecting vehicles and pedestrians in vehicle from camera simultaneously. So in this model, we can label the vehicle and pedestrians by a yellow block. You can see in the picture, the car is labeled by a car, and the truck is labeled by a truck, and pedestrian is labeled by a pedestrian. And this model is also powered by automatic driving system toolbox.
I'm Hao, and I'm going to introduce you the state flow decision making of the vehicle. The first state flow diagram are the roads and the stops, are the critical checkpoints for the bus. Turnings or stops may be required at these checkpoints. Between these checkpoints, we have additional state flow diagram for checking if the vehicle is facing signal, stop sign, or crosswalk. Within Eastern Town Center area, the traffic will be super busy, and we need special checking to ensure the safety of the vehicle and the passengers. The bus stop logic will be used for all the bus stops in this area. The team wants to ensure the vehicle is fully stopped before the door is opened, and check the surroundings before the vehicle leaving the bus stop. The last state flow diagram was created for the lighting and lights. It is meeting the requirements of traffic regulations and for the safety of passengers, pedestrians, and other vehicles on the road.
Hello, this is Shilin Shao again, and this problem is real-world implementation challenges. We divided the challenges into three parts. The first part is weather. For example, the rain can affect the sensor, lead to slippery roads, and make the vehicle hard to detect the obstacles in front of the automatic vehicles. And the thunderstorm can also affect the sensor, damage the electricity and electronic devices on the vehicle. And the snow can lead to slippery roads, and light reflected by the snow on the ground will affect the visible of the camera, and the wind can affect the longitude and lateral control. The sandstorm can also affect the sensor, affect the visibility of camera, and hard to detect the road obstacles on the road, and cloudy can also affect the visibility of the camera. So we ranked them by the risky level. The rain is 1.5, thunderstorm is 3.5, snow is 3, wind is 0.5, thunderstorm is 4, cloudy is 0.5. The second part is the traffic. For example, if there's too much pedestrians on the road, it will be very hard for the vehicle to detect them, and the routes of the pedestrian are unpredictable, which will lead to a difficulty of decision making and lead to an accident to the pedestrian. So we ranked the risk level to 3. And the second part is cars that disobey the traffic laws. So some cars disobey the traffic laws will lead to the hard to avoid them, and increasing the difficulty of the path following of the automatic vehicle, and hard to determine the accident responsibility. So we ranked it as 3. And the third one is visible traffic signals and fine. It will increasing the difficulty of path following and more likely to disobey the traffic laws since the vehicle can't detect the signals and signs. And the first part is the traffic control. So if the traffic is controlled by the police, the vehicle may be hard to apply the control. And the fifth one is traffic jam, and it's very hard for the vehicle to select optimal routes to the destination, but it is not very dangerous to the vehicle. The next one is accidents on the road. It is very hard to detect the vehicles and people in accidents, so it will lead to a new accidents. So we rank them risky level to 4. And the next one is irregular vehicles. Some vehicles are hard to detect because they are irregular shapes, so we rank them as 3.5. And the roadblock is also hard to detect. And the new traffic law and fine, some states will publish a new traffic laws, and the vehicle will have no update the law in a short time, and let the vehicle to disobey the new traffic law. The last one is multiple rules compatibility. So for the vehicles in different countries or states, it will increase the difficulty of decision making because they have different traffic laws. The third part is other challenges. For example, the extreme environment. It will affect the sensors, the longitude and lateral control, and the lifetime of electricity and electronic devices on the vehicle. So we rank the risk level to 2.5. The next one is broken road. Some road which is broken is hard to detect because the range of the LiDAR and radar is limited, so we rank the risk level to 4. And the third one is road with water and ice. It's also very hard to detect because of the limitation of the sensor. The fourth one is extreme contrast of the condition. Some high contrast condition is hard for the camera to detect the obstacles on the road, so it's also very dangerous. The last one is unusual obstacles. So some obstacles are hard to detect because it's unusual shape, and it will lead to accidents to our automatic vehicle.
I'm Sean again, and in conclusion, a standard shuttle bus was selected as our vehicle, and the parameters for this vehicle were determined based off technical data provided online. Speed control was implemented to make sure the shuttle bus doesn't exceed the speed limits of 15 miles per hour, and the path following model was designed for the route of Easton, along with a collision avoidance system and a simple state diagram for decision making.
So here are our references. And our contact information. We are Group 3, and thanks for listening.